perhaps its most important functions is that this will serve as the public defense for Philip Muscarella's dissertation. Now, before introducing the speaker himself, I'd like to acknowledge several distinguished members of the audience. This includes Bruce Lippard, who is co-director for Philip, Mike Cosrow, Professor Mike Cosrow from the Oregon State University, and Professor Fabrice Barone, who's the committee member from the department. The fifth committee member, Professor Paul Wong, unfortunately could not be here. He has a family emergency in Taiwan. Now, Philip, let me tell you a little bit about Philip. Philip is a proud native of Buffalo, despite their miserable pro sports record, with the exception of the Sabres. He received his bachelor's training at John Carroll University in Ohio, and he's been here at the now School of Marine Science and Policy since 2006, working on the HF radar project, mostly with Bruce. In this project, he's had experience in going out and digging trenches for cables, on a rowboat, taking antenna pattern measurements, and also in developing very sophisticated analysis techniques, theoretical analysis techniques to look at the data. He's also had to interface with other groups within the university, particularly the geology, working with the geology department on ADC deployments. He's also now a master ADC deployer. And with Dana Barone's group in combining atmospheric model data with ocean current data. So all of this experience has given him a unique picture of the circulation in the Gulf of Mexico, which he will describe.
Delaware Bay.
Gulf of Mexico, sorry, Delaware Bay, whatever. Logically, they're equivalent. Were you a little worried about that?
5 minutes. We need 5 minutes to prepare.
Okay, so the title of the dissertation is the Circulation in Delaware Bay from the Lagrangian and Eulerian perspectives. Now, since this is a dissertation defense, there's a bit of protocol. Oh, we got him.
Someone just called.
Okay.
Hey there. Hey, Zach.
There is a bit of protocol. We'll have in the open session, of course, as the audience does here, pipe up immediately during the presentation with any questions on clarifications. And afterward, there will be an open, as we usually do, a question and answer session with the candidate. When everybody's exhausted from that, we'll have a short recess, and then the examination will continue in an executive session with just the committee members and Philip. So, Philip, the floor is yours. Tell us something that we don't know about Delaware Bay.
Okay, I'll try it. All right, I'd just like to say thank you to Denny and Bruce and Fabrice and Mike for helping me over the last 5 years, 4.5 years. It's been a ride. All right. So, circulation of the Delaware Bay mouth from the Lagrangian and Eulerian perspective. I just like this picture. It's from our radar site at Cape May, New Jersey. If you look real close, you can see Bruce in his red shirt right there. Also like the left. Just a quick outline, introduction, the data sources that we're using, some comparisons between the data sources. We'll go into the Eulerian perspective, the Lagrangian perspective, and then some conclusions. And the picture of our other radar site. This is the one at Cape Hamilton State Park. So just a quick introduction of the Delaware Bay estuary. It's located right here along the middle of the eastern coast of the United States, New York, Philadelphia. The red box is just the general, Delaware Bay estuary. It's partially mixed, highly driven, has a persistent estuarine outflow, the strong annual outflow in the spring months caused by runoff, and there's some rough topographic effects, especially near Cape May, New Jersey, and I'll show that in a second. And most of the previous work in this area has been done by Rich Garvine, Andreas Monschau, Paul Wong, and others. Here's just a topographic plot of the Delaware Bay and the adjacent shelf, and this black outline is representing our general region of interest. The blue colors are obviously deeper depths, and the red are shallower. And you can see I was talking about the rougher topography around Cape May, and then there's this deep channel near Cape Hamilton in the north. So here's the why do we care slide. Well, the Delaware Bay estuary is an important port system, Philadelphia, Port of Wilmington. It's also responsible for a large injection of fresh water into the mid-Atlantic region. And we're going to be examining some high-resolution synoptic data sets which are going to provide a good amount of variability and resolution in the coastal ocean. Here's some topics that we can look at: search and rescue, oil spill prevention and response, deep water horizon, harmful algal blooms, ecosystem studies, and this is just a picture of a shipping terminal in Philadelphia.
Oysters.
Yes, blue crab larvae. I'll throw that into ecosystem studies.
Oh.
No?
I call it food.
Food? Okay, food studies. All right. So why the Lagrangian and Eulerian perspectives? Well, first let's start with the holy grail of equations, F equals ma. And then we're going to perform this first integration to get to our velocity data, this is the U. And this is going to be representative of an Eulerian frame of reference, where we're looking at points in the ocean and examining the fluid motion around these points. So a typical Eulerian question would be, what are the forces acting on the piling of an offshore wind turbine? That's very relevant to the Delaware Bay with this blue water wind project being installed. This kind of forces the currents that are acting on this piling. And then there's this second integration to get to the Lagrangian framework. And here we're going to be looking at the trajectories or pathways of a single particle through the ocean. And a typical Lagrangian question here would be, what does an oil spill, or where does an oil spill go? How long does it take to get there? Where do these blue crab larvae go? How long does it take them to get there? Those types of things. Transport questions. All right, now a little history lesson. Previous work on the Delaware Bay. Andreas might recognize this picture. It's from his 1992 paper of the astronomical tides at the Delaware Bay mouth, specifically M2. It's where we see that M2 is responsible for 90% of the tidal current kinetic energy. And in this figure, he's showing from a large record of current meter data the semi-major and semi-minor axis of the M2 tidal ellipse. And you can see right near the mouth, for these current meters, they're very rectilinear and elongated, and then as we move offshore, they start to decrease in magnitude. And this is also validated by a Whitney and Garvine 2008 paper, where they used a tidal model for the Delaware Bay to produce. They're showing the semi-major axis of the M2 ellipse in blue with these historical ellipses from current meters in, I'll call that magenta, in the background. And they agree relatively well. Okay, moving on to the buoyancy-driven flow. Here we have a figure of current meters from the Garvine 91 paper deployed in an arc around the mouth of the bay. And what we want to show is the kind of classical estuarine flow where we see the near bottom, the near surface outflow and the near bottom inflow into the estuary. And the red triangles are the near bottom, the yellow are the near surface. And the triangle represents the 95% confidence of the payment. So now into my kind of specific questions that I'd like to ask from the research here. So first, we're going to do some Eulerian questions, and we're going to look at just spatial distribution of the currents. What does that look like? Then spatial distribution of the tides. How does the HF radar data help to fill in this tidal picture? Also, we want to see the wind response in the surface current record. And also, we observe this cross-mouth current, and we would like to examine it in some more detail. So, assign some characteristics to this feature. Moving on to the Lagrangian section, we're going to examine some progressive vector diagrams and how useful they are in the coastal ocean. And then into some resonance times and escape fates. So really, again, these transport questions that I was mentioning before. And lastly, blobs. What are blobs? What can they tell us in the coastal ocean? So one of the first types of data that I'm showing here is just the Delaware River discharge at Trenton in meters cubed per second. So this is just an 8-month record of discharge in, like I said, cubic meter per second. And this record is showing just kind of the general time period of the analyses that we're going to be looking at throughout the talk. And for some of the analysis, it's useful to divide it into kind of a low and high outflow period. So for this for this example, we have a low outflow period of 45 days from early October to mid-November, and then another 45-day high outflow period from early March to mid-April. So just something to keep in mind as we're moving on through other analysis throughout the talk. Other data sources, ACPs, station winds. The ACPs here are represented by the black dots. We're using 3 RDI, upward-looking, bottom-mounted 600 kilohertz ACPs, which are going to be used to compare with our synoptic data sets, and also some wind station, Brandywine 44009, also for validation of our wind model. And we're really going to only be examining the nearest surface bin for these ADCP deployments. Okay. So now moving into the WRF, which is our weather research and forecast model. It's going to be providing, first it's a regional scale model that provides 10-meter winds at 1-hour spatial resolution. This model is run and configured by Dana Verone, Neil Barton, Chris Hughes, and we're going to be using it to, we're going to use low-frequency winds to examine the wind response in the surface current record. And there's 3 nests for this model. The largest nest encompasses the whole mid-Atlantic region. It's not being shown, but the 3rd nest is the one that we're really going to be examining. Yes?
Why use model winds when there are plenty of good records from environmental buoys that are actually in the water?
They are good records. The model really has this spatial variability, which is what we're interested in. So we want a synoptic record of winds. You can't get that with stations.
So you will be addressing spatial variabilities in the wind field that are important?
No. But we want it.
It would be nice.
It would be nice. It would be nice. But we're really interested in its influence on the low frequency winds influence on the surface current record.
Okay, then let me rephrase. Is there significant spatial variability in the wind field that is important with regard to the circulation at the bay mouth?
Is there significant
spatial variability in the wind field that is important for the circulation at the bay mouth? Because that would be your justification. That is your justification of using model output as opposed to data.
Well, first, we have no station winds within our HF radar coverage.
If there's no spatial variability, it doesn't matter. If there's a wind station that's actually measuring winds 5 kilometers away or 10 kilometers away.
Well, I think I'd say there's a small amount of spatial variability. I think there is some, but I'm not sure that it's... We've done correlation or comparisons between single points and the HF radar data, and they've been good, but I think the local winds from the model are better. You get better correlations with the surface winds. All right, so HF radar. And can we keep the big science questions to the end? Just clarification. Okay. HF radar. So we have 2 standard range CSONs, 25 megahertz, which are going to be providing hourly 1.5 kilometer surface current data for that 8-month record is really what we're going to be examining. They've been operational since December 2006, and what we see here is temporal coverage in time of our HF radar data. Environmental effects can cause the HF radar data, especially near the boundaries, to drop in and out. So what we're classifying as a valid data point are all these black dots, which are at least 80% covered in time. And this black bounding polygon is going to be used for some other measurements as valid data points. And just to get a kind of look at what a surface current map looks like for the Delaware Bay, this is an animation. Yes, it is. An animation of just surface currents for one day in early October 2007. It started on an outflow, and you can see this strong M2 signature in the currents as it changes direction as it flows. So just to get a picture of what we're actually examining with these HF radars. And you can also notice certain vectors appear and disappear, especially on the boundaries. So the data comparison. So is this HF radar good data? Well, we made a comparison between the ADCP at location C. Well, we did it for all the ADCPs, but I'm only showing location C. And between the HF radar, which is in red on these top two time series plots, and the ADCP, which is in blue. And this is the nearest HF radar grid point to the ADCP location and the nearest surface bin of the ADCP. So we see a strong M2 signature and very good agreement. This is the scatter plot for the U and V, and again, we see very good agreement. It's approximately 7.5 centimeters per second RMS differences. So now moving into the tidal picture. This first figure I'm showing here, which is a color plot, is the variance due to the tidal fit divided by the total variance of the surface current record. We multiply that by 100, and we're calling it percent variance due to the tides, or the top 5 most energetic constituents of the tides. We compute our tidal fit with a MATLAB T-Tide toolbox. It's an 8-month tidal fit from October 2007 to May 2008. And what we're seeing here in structure is that near the mouth, we see that 90% of the total velocity in the currents is due to the tides. And as we move offshore, it starts to drop down to, say, approximately 40%. Okay? And this is one of those kind of neat plots that it might be difficult to produce with a collection of point measurements. You don't get the type of spatial variability that you see in the HF radar data. So here we have just the M2 constituent. This is the HF radar ellipses, which is in red, and again these historical current meter data from the Munchausen 92 paper in black. And we see good agreement between the two. Their orientation is relatively the same. And like I mentioned before, the ellipses tend to be along or rectilinear near the mouth where the tidal energy gets focused, and then as we move offshore, they start to become more elliptical. So this is just a comparison between this M2 tidal model and our radar data. This came about because of a comment to a recent paper, and I showed the tidal model in the early, that's from the Whitney and Garvine 2008. So this figure up here is showing the semi-major axis of the M2 tidal ellipse for the model minus the radar, semi-major axis of the radar for M2, normalized by the radar. So we see here, for a large portion of the domain, the model is underestimating the semi-major axis, which is, probably because the model is actually reporting depth average velocities. And we can also see kind of a overestimation here near Cape May, which could be due to large changes in topography, rough topography effects causing problems in the model. If we look down at this second...
It could also be because that's where the radar data is not as...
that is true. It's a baseline region. It becomes more difficult to get good data there too. Right, don't want to just put it all in the witness thing. Okay, so this second figure right here is showing a comparison between, again, the model data in red, the major axis of the ellipse, and the radar data in blue along this black line moving offshore. So we see for the majority of the area where they line up, it's a very good comparison. All right, now moving beyond the tides into the subtidal picture, we have here just monthly mean for the surface currents for October 2007. So some of the features that we can examine in this mean picture is first this outflow plume, which has been examined by Garvine through multiple papers, and then also this crossmouth region that's flashing red. This is the crossmouth current that I mentioned before. It hasn't really been examined in any detail in the literature. It's just been hinted at by Long and Moses Hall. So one of the questions, or two questions that we're asking is this flow persistent, subtidal feature, and does it vary seasonally? So to go about answering that, we show, again, these are mean currents over the high and low outflow period, and we're showing here that the mean currents in the high outflow period are slightly larger than in the low outflow period. So this may indicate that the outflow, this cross-mouth flow, may be forced or by the injection of fresh water into the mid-Atlantic region.
You don't mean more than just Delaware Bay? Or?
Excuse me?
Well, you said the mid-Atlantic region.
Well, inject fresh water that could be flooding down the New Jersey shelf.
Okay,
There's
right.
non-local advection that could be
It's not just
propagating
in
into our
Delaware
domain.
Bay.
Right, not just Delaware, yeah. Okay, now into the wind picture. Well, this is for just, this is a vector stick plot for the WRF 10-meter winds at a location in the center of our HF radar grid with, this is 40-hour low pass, and also the surface currents, which have been 40-hour low pass, and we're examining just a single point in time. So if you look at this record, we see that it's very episodic. There's multiple 3 to 5 day events where there's changes in wind direction and magnitude, but we do see some vector, we do see some good correlation between these 2 points, and here's on the bottom is the angular difference between these, and where the red values are the currents to the right of the winds. Okay, so we're saying that we do see a correlation between these two values, but the episodic nature of the wind record during our time periods, this is just the high outflow period, makes it difficult to set up a consistent Ekman response. Yes?
You have a complex correlation value of 0.85. Is that R or is that R squared? Is that the variance explained, or is it just the correlation coefficient?
That is from the complex correlation from Kundu. It's a correlation of 2 vector time series, and it's the amplitude of that.
Okay.
And then there's the veering angle of with the currents to the right.
Yeah, that would be my next question. But first, is this the percent variance explained, or do I have to square that in order to get kind of the percent variance that's explained?
I think this is just your R value.
Okay. Yes, that makes sense. Good. What's the angle that you get out of this? Because of complex correlation.
Oh, the varying angle between the two? Well, it does change, but...
no, if you have one record, you get one correlation coefficient. And you
well, I'm saying for the high and low outflow periods.
Sure.
Right. But for this, I'm going to show that the spatial variability of that in the next slide. So if you see here, this is the plotting of that complex correlation I was just talking about over the whole domain for the HF radar and the WRF data points. So here's the amplitude of the correlation. Here's the veering angle between the 2 vector time series. You can see in the area where minus, in the outflow plume area, you see kind of lower correlations between the winds and the surface currents, which is kind of what you'd expect in the plume region, which is wouldn't be forced by the winds as much. And then over a larger portion of the domain, we do see kind of higher correlations. So, but as far as the angle between them goes, we see this kind of interesting banding effect here, where the currents are actually to the left of the winds in this area and this area, and then slightly to the right in the center portion of the domain. This is slightly inconclusive. Okay, and which we see the same structure in the low outflow period. Sorry, that was the low outflow period. This is the high outflow period. So again, in the high outflow period, you see kind of a decrease in the amplitude correlation throughout a larger portion of the domain. Like especially even in this cross-mouth region where I mentioned that we saw this cross-mouth current. So maybe this, again, is another inkling that cross-mouth might not be forced by, yeah.
Can you just go back one more? I was interested in seeing whether your regions of blue veering angle and red veering angle are somehow related to where you get high complex correlation.
Right, yeah. Like if you have low complex correlation amplitude, then why would you even trust the varying angle, right? Yeah, so maybe in this region right here, where we have kind of lower complex correlation, why would you even trust this kind of veering angle where the currents are to the left of the winds? That's a valid point.
Have you looked at what the veering angle is only in the regions where amplitude is above X?
Not specifically, but you can just look at this plot and say that, where we have good complex correlation amplitudes, we generally see the complex, the currents are to the right of the winds. So, yeah. Kind of same thing goes here. This general region, this general region.
So you've taken the mean out both from the wind and the
It's been low pass filtered. So yeah. Wait, no, sorry. Excuse me?
Oh, so this is low pass filter.
Yes.
Have
So
you taken
40
the mean
out. Have you taken the mean out of the low pass filter
Yes.
record?
The record mean.
I think so. Yes. Yes, I think so. Okay. Now moving into the Lagrangian section. Well, to compute Lagrangian trajectories, we have to have a completely filled-in record of HF radar data. And what we're using here to fill in the gaps in the HF radar data is open boundary modal analysis, which has been developed by the Delaware Bay research group. They have this MATLAB toolbox called HFR Pros and OMA. So what we're showing here is just an example vector comparison between the OMA and the HF radar, the OMA being the black vectors and the HF radar being the red ones. And we can see we have a relatively good comparison over the majority of the domain. So really this is just a tool for filling in the gaps in the HF radar record. Okay. So how do we actually compute trajectories? Well, let me start this animation because it's one of my favorites. We're computing we're integrating velocity equations with an adaptive time step Runge-Kutta, MATLAB ODE45, and performing linear interpolations in space and time, inter n. And what this animation is showing is a particle being released from each of these 3 green points every hour, and then the particles advecting through the domain, being forced by the OMA currents, that's what these are here, and they're being colored by the amount of time that they're spending in the water. So you can see this, and if a particle reaches a boundary, it's just being removed. It can't return back into the domain. So it's really, I like this plot just because you can think of these as almost a streak line. And you can see the points start to spread out as they leave the initial locations and then start to move north, some staying in the domain for 100 hours. Okay. So next we're going to talk about progressive vector diagrams. This might not be a totally intuitive product to use, especially for a physical oceanographer. They might not think, oh, this is something I want to use. But for ecologists, they're very interested in this for some reason. But this paper, Epifanio and Garvine, or Epifanio et al., which has Rich Garvine as an author, shows a progressive vector diagram, which is they're using a current meter at this location right here and taking the velocity time series and placing the vectors head to tail as a kind of circa transport type product. So for this example, they're equating it to a blue crab larvae that is spawned at the Delaware Bay mouth and then moves north, starts to turn into New Jersey, takes a ride on the Garden State Parkway, and then moves offshore somewhere in the diagram. So the progressive vector diagram, that's what this head-to-tail vector placement, is really only valid in regions where the currents are spatially uniform, so it may not be useful in the coastal ocean. So here's some possible uses. And what we did is we compared a progressive vector diagram in this example right here, for vectored for 12 hours versus trajectory that we computed with the HF radar diagram, HF radar data for 12 hours. And we're tracking the time it takes to separate these particles or these data products by 500 meters and 1,000 meters. So this is an animation. And this is for 9 different initialization placements in the center of our HF radar footprint. And we can see how long, or how far they separate after 12 hours. So if we look over here at the separation statistics, we see that majority of the particles will separate by 500 meters in 12 hours. And again, the majority will separate by 1,000 meters after 12 hours. There are some points that do stay together longer. This has a long tail. It's not being shown. But what this is saying is that the progressive vector diagram may not be the most useful tool for representing transport in the coastal ocean where there is large amounts of spatial variability, at least not on time scales exceeding 12 hours. Now into the resonance time results.
Can I ask you?
Yes, Denny.
A question on that. So, if you were to take, say, 2 current meters a kilometer, a couple of kilometers apart, or a couple of radar pixels a couple of kilometers apart, you probably wouldn't come up to. Would you come up to the same conclusion, but just by looking at the correlation between 2 adjacent current meters or 2 adjacent radar cells?
I think you need that spatial variability to make this.
Yeah. Well, my impression is that they would be highly correlated for a long period of time.
Well, the two, we recently did this for the 2 HF radar grid points right next to each other, and yeah, they do stay together.
So
very long.
So this would not have been predicted from just looking at the Eulerian correlations then.
Right.
Okay.
Okay. So resonance time. Well, first thing, how do we compute resonance time? Well, we are initializing a particle at every one of these black locations inside this grid and tracking it until it reaches this red boundary zone. And once a particle reaches this boundary zone, it is termed escape, and it cannot return. So to compute the resonance time, we just subtract the time that a particle escaped minus its initial time. And that's the resonance time. We've computed 3 months of hourly resonance time results and have yielded approximately 6.3 million trajectories. So let's take a look at the sexy resonance time plot. On the left, this is a p-color, or just a color plot of the resonance, where red values are high resonance. That means these particles are going to remain in the domain for in excess of 100 hours, and then particles here are slightly less as you move down. And on the right, this is the escape phase plot, meaning particles that are initialized in this red region will eventually leave the domain through this red-colored boundary segment. Okay? So you can obviously notice the effect the tides are playing on these particles. you see that all the particles initialized here are going to leave the domain relatively quickly, so they would hence probably exit the domain into the bay. We also see, it's really interesting to kind of look at features that appear in the residence time plot and in the escape fate plots. This is, yes?
So, just so that I understand this right, so it's a
Sure.
clarification question. So, what you're showing is that the residence time, because the Lagrangian property depends on the time and the location of the particle that's being released,
Yes.
as well as the domain shape.
Yes, it does depend on the domain shape. The magnitude of the residence time would obviously depend on the domain shape.
Considering that's so variable, why is this a useful property?
Excuse me, what do you mean? What is so variable?
What's wrong? I keep that for me. Sorry. That was
I'll go. No, let's do it. Let's go.
Let's
do it. So you're saying that what's so variable? The domain shape?
No, because it depends. I mean, the residence time depends on the time within the tidal cycle, say,
right,
as well as the location.
Right.
So it's just as variable as velocity.
Sure. What's the point? What's wrong with it being variable?
Well, I mean, residence time, I mean, maybe as Danny calls the Eulerian biggest, they like it to be constant.
What do you mean? What do you mean they get to be constant? He's taking offense. You don't want to come back.
So maybe the bigots have learned something.
So you're thinking of residence time as very like a single quantity, and you.
Well, that's what the ecologists think.
Well, then we should tell them something too. Let's get them in here. Where's the epiphony? But no, it's good to. I think it's good to show the type of variability that you can see even in this small tidally driven domain in residence time.
But the message really is that kind of the residence time with this domain can be anywhere between half an hour to 2 days.
Sure. Well, you know, Bruce was mentioning this before. If you think of this as kind of a lower bound on residence time, and you change the shape of the domain to a larger area, this is as big as we get. We don't get any more data.
Okay.
You know, if we had larger, we'd make it larger. Yeah. So if you think of this as a lower bound, and you redraw the boundary size, it's not going to get any lower than that.
Right.
Right. And I was also talking to Helga about this earlier. She did some comparisons in residence time for model data where she had a large domain and then shrunk the domain to a smaller size. You see the same structure in the residence time values as you see in the large picture as you do in the smaller one, but obviously the magnitudes would change. Good? Oh, yes?
Just the color scheme, the red is...
the red's 100.
47, right. So that's
Well,
roughly 5
some of
days.
these are actually higher than the...
Right. So it's roughly 5 days up there, around about 1 day.
Yeah,
Less than 1 day.
yeah, let's yes.
So why does the domain look so irregular shape?
Well, that's just because of the HF radar coverage. Each HF radar site is on a polar coordinate grid. Okay, so because you can only see radially towards or radially away from a single HF radar site, and you can't get information that's looking directly towards another site. They're looking at the same angle. There's geometric delusion of precision effects. The GDOP is the term. So it's just kind of the shape of the coastline, shape, and the type of radars that we're using just causes this shape of the domain. And we're saying that valid grid points are 80% coverage in time. That kind of drew this outline for us. Okay. So just to look at here's this single value, a mean of residence time for several months. Just to look at some of the, if we see any kind of characteristics in the means. For the 3 months that we examined, March, April, and September of 2008, we see that kind of lower residence time values for the higher outflow months than we do for, say, September. And this could be due to like a flushing effect of the domain by the outflow plume due to the higher runoff in the spring months. Okay. So this is a kind of a new product that we've been throwing around. We're going to say that the probability that any particle remains in the domain beyond a certain time is going to decay as time goes on. All right. So if you take all the residence times for a certain month and you bin them into how long they remain in the domain for, we're going to show that the number of particles in the domain at any time over the number of initial particles is going to decay. And in our case, it's decaying exponentially. The exponential with a very good exponential fit of 0.99. So, and then a decay constant of 1 over lambda of 32.8 hours.
So is there some significance to the 32.8 hours? Tell me something about the probability of something getting flushed out.
Well, after 32.8 hours, approximately, E particles are going to be left in the domain. So, to be determined.
Well, what is this? What I'm really asking is there any significance to the 32 to the 33 hours?
It's still working on that. We're not really.
Okay.
I'm not really sure exactly what the 32.8 hours is yet.
Well, I don't think it can, because it depends on the domain shape. So you change the domain, and that e-folding scale changes. So space and time
but
scale
for
are
this
coupled.
domain, he gets a number that.
It keeps it there. Well, there, I think it's happening.
Okay.
So he's right. Like if you increase, if you did the residence time for the whole Atlantic Ocean, the North Atlantic, what would the e-folding time be for that?
Well, if you increase the size somewhat on this, it's not clear this number will change in the Delaware Bay region, since this is an integrated effect.
I think if you increase the domain a lot, though, you could start seeing. So you're trying to.
But you've got more particles in there.
Right. Well, you're also trying to interpret this one value over millions of integrated quantities over a domain that we're addressing has tidal effects, wind effects, plume, outflow effects, and you're trying to say this one value. What is that? What kind of feature does that represent?
I'm not sure this would
difficult.
change if you have radar coverage within the bay, or your domain extended into the bay, or extended a little further outshore.
Right, because you're still looking at
because this is one integrated quality for all the particles that are lost in there. So it's as long as you're in a tidally forced region, I would suspect this number wouldn't change very much at all. It would not be as dependent upon the domain shape or size.
Well, I think then
maybe.
Yeah.
We'll come back. Yeah.
Sorry to keep harping on this particular slide. You said that the shape looks similar for different months?
Or no. You get the same feature, the same kind of exponential decay.
You get exponential decay. Do you also get the same lambda value?
Within 1 hour. Yeah.
And
We're gonna eventually look at like single hours and see how that changes in time. Look at different time scales.
that was going to be my next question.
Okay,
You
yeah.
looked at how it changes for the title.
Right. Exactly. Yeah. No, that would be. We're gonna look at that. Yeah. We have more residence time results. Different times of the year. Like I said, this was new. That was new results in the last week or so. So now, on to the last Lagrangian topic is estimating surface flow deformation from finite area blobs. We're going to initialize a circular collection of particles along right here in this region. It's a blob with a radius of, I think, 3 kilometers. And we're going to advect it through the domain for approximately 115 hours. So let's see this movie. And notice how the blob changes shape and area, how the perimeter changes. Initially shrinks, and now it's going to start deforming and spreading out into this kind of long, thin filament, which is interesting. It's kind of the effects you see in dye patches as you deform, they start to become these long, thin filaments, and then it loops back on itself. Okay, so we're going to ask some questions like, how does the area change in time? How does the perimeter change in time? And what are some kinematic quantities we can examine around the blob as it's moving through our domain? So first, like I said, the blob is just a circular collection of particles that's connected by line segments. We're cheating and initializing our blob in a high area of residence right here. So we just take a residence time plot, find an area where we have high residence, and bam, smack down a blob that stays in there for 100 hours. This was a lot harder before we had residence time. So here's a time series plot of the perimeter of this blob as that's been normalized by the initial perimeter as so I pointed out that we saw the blob initially shrink and then turn into this long, thin filament, and that's kind of what you see here. So area, there was an initial increase in area, and then a decrease relatively rapidly, and it stayed relatively constant for the rest of the.
Looks like you have potentially another e-folding time scale there for the area.
There could be. There's a lot of variability in this too. There's a lot. We've only looked at several examples, but they can be very different for each one. So. You know, it's moving in space and it's changing shape and orientation, so there's a lot going on.
So the area is decreasing, but the perimeter is increasing.
Right.
Okay. Just.
Yep. That's what's happening with this long. Seems counterintuitive, but yeah, as you saw, that's happening. So using several methods, we can calculate some time series of these kinematic quantities, divergence, vorticity, normal, and shear deformation. All these values are being normalized by the local Coriolis, and what we see is just some relatively noisy quantities, but if we, especially in the divergence and the vorticity, if we look at these values in frequency space, it can start to pick out some features a little bit better. So if we move on to the power spectra of these quantities, we see some pretty strong peaks over, this is the black line is the 95% confidence interval for these quantities. We see some pretty strong peaks in the deformation quantities in the semi-diurnal band. And we also see almost twice the semi-diurnal peak in the divergence plot. So these are, we're trying to kind of interpret these results based off of, some of the things that are happening at the bay mouth with our respect tides. So we think that maybe the deformation, it's being deformed. We see the strong, you can kind of see the, semi-diurnal frequency in the normal and shear deformation.
This would be relative vorticity, right?
Yes.
Yes, that's right.
So if you go back, at the tidal time scale it reaches 0.5, but if I put a low pass filter through that, that would be much smaller one, right?
The quantity, you're saying how high? Oh yeah,
Relative.
right. It would shrink, yes. I think you'd lose a lot of the structure in this, but I think that would be interesting to see what it does after filtering. But again, the gradients here are being calculated from small differences between the velocities, so. Okay. All right, the conclusion slide. I know everyone wants to get out of here and go out and play in the nice sun. So first, we feel that there is this kind of increased utility in having these 2D plus time, high-resolution synoptic data sets in the coastal ocean, and we're seeing how the increase in resolution is playing into our analysis of progressive vector diagrams, residence time, tidal calculations, etc. The tidal current picture has been established by Andreas and others, and we're kind of filling in the gaps in this tidal picture just by showing some of the spatial resolution of the tidal ellipses. We've identified a cross-mouth flow in the subtidal picture, and it is a persistent feature throughout all the monthly records that we've been examining, and we're still not sure of the forcing mechanisms behind this flow, but we've just taken a first step at kind of characterizing it and identifying it. The presence of all these other forcing mechanisms, tides and outflow and episodic winds, have made it difficult to isolate a consistent wind-driven flow in the currents. We're kind of inconclusive in this banding effect of the veering angle between the surface currents and the wind stress. And moving into kind of the Lagrangian conclusions, we're issuing this kind of caution to the ecologists who are interested in using PVDs as a transport value in the coastal ocean. We accept that the PVD isn't always used for that, but since that paper that I showed with the crab larvae taking a hike on the New Jersey Turnpike, that's been cited over 100 times in the literature. So if people are using that value as the truth, then they may want to consider the spatial variabilities in certain regions, especially near the coast, because they can have an effect. As far as residence time goes, we have this small tidally driven domain, and yet we're seeing relatively high residence time values, which could be due to the certain groupings of particles being just conservatively moved back and forth by the tides. But this is a very valuable metric for anyone interested in looking at transport questions, like I said before, the crab larvae people, the oil spill technicians, whoever. And lastly, these blob examples that we looked at were fundamental in visualizing the shape and orientation changes in the coastal ocean. Okay. So what's next? What could be done? What else could be done? Well, again, I mentioned that before. We'd like to know what the origin of this cross-melt flow is. There could be some interesting things. Maybe it's tidal rectification. Maybe it's this non-local advection I mentioned. We're not sure. So, what causes the differences between ADCP and radar currents? The ADCP is averaging on time scales of minutes and spatial scales of meters, where the radar is averaging over hours and kilometers. So the differences in time and space scales can add to kind of observed differences between these two data sources. We actually have a very good comparison, but there are some observed ADCP and HF radar comparisons that aren't quite so good. So what are causing these differences? How does transport change with depth? Well, I think we need a lot more ADCPs than we currently have to answer this question at the bay mouth, to get just some more data, and then maybe kind of use it to draw some conclusions with HF radar data as kind of this upper boundary of the in our region of interest. So also looking at this, how do winds and river outflow influence residence time? Well, residence time is a very integrated quantity, so it's sometimes difficult to assess forcing mechanisms to these particles in our region beyond the tides. And lastly, how important are the blobs, or the deformation processes on the blobs, in this kind of evolving surface flow? What is causing this filamenting in the ocean? What is causing convergence or divergence? We would have liked to have dug into the blob question a little more. All right, so this is kind of just a slide of where some of this work is being put and published. But that's it. Thank you.
Questions, anyone? Louis? Questions?
Yes.
So you're modeling, especially with your residence time and how long the particles stay in a box. How reliable is that from year to year? Like, I think this was a compilation of several months. out of the year, or how long is that, but is that something that can apply on year-long scales? And I just don't know much about the topic. Is that with our winds, are you able to track winds over year-long scale?
Like, you mean track particles over the year?
Or just, would that pattern be the same year after year?
You mean in the same months, or say like
Right,
mean
in the
or
same
something like that?
month.
Okay. Well, the time period that we examined was where we had the best HF radar data. So we don't have as much data in other years as we'd like. There's some problems with the radars themselves that have occurred, broken wires, et cetera, et cetera. So, I think that you would see general patterns being the same, and the tidal effects, again, being very important in what your residence time values are. But like we were talking about before with Andreas, I think it's important to acknowledge the amount of variability you see in this residence time plot. So I'd be hard-pressed to make any general statements about the residence as it, from month to month beyond just very, you might see lower residence in the high outflow months versus some of the lower outflow months. Okay. Yeah.
Till the end, you said that the ADCP data and the radar, the HF radar data are averaged over different time scale and spatial scale. But I don't understand, because I think when you measure something, it's just like a function of pulse. But maybe because there are noise, you need to remove the noise, so you have to average over.
Well, the ACP is this acoustic pulse, right? And it's scattering back up particulate matter in the water column, right? So you acknowledge that it's a small area that we're looking at, meters, right? And you can get resolution in 5 minutes if you wanted in the temporal space. Yeah, like you said, there is averaging for the radar as well, but it's both in space and in time, where the radar is emitting surface waves that couple with, or it's emitting EM waves that couple with the ocean surface, and then scatter off waves that are exactly 1/2 the wavelength of the scatter off ocean waves that are 1/2 the wavelength of the transmitted EM wave, and that'll